Hi there, my name's Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech. At Georgia Tech, I run a team of students called the Retrofuturistic Hardware Vertically Integrated Projects team, and we're doing a bunch of cool, interesting things. And one of the things that we're working on is to follow up on my dream to build a computer themed around the year 1987. That's the year I was a junior in high school, but 1987, I think, is a sweet spot for technologies for making a homebrew computer that still is sort of reasonably modern and usable, like the PS2 format for keyboards and mice came out in 1987. So I'm primarily recording this for the benefit of my retrofuturistic hardware students, but I'm posting this to YouTube, so maybe other people will find it useful as well. And basically what I'm going to do is I'm going to bumble around with some real-time engineering and do what I would normally do anyway, sitting with some data sheets at my kitchen table. But I'll record myself doing this and talk out loud while I'm doing this. So obviously this isn't planned. This is not going to be edited in any significant way. It's not going to be as polished as my regular lecture presentations that I do for a regular class. Anyway, the idea here is to build a computer built around the Western Design Center W65C265. This is a microcontroller built around the 65816, which itself is a 16-bit extension of the 6502. In particular, what I want to do is I want to build something based around the development board they have for it, this 65C265SXB. The SXB indicates the development board. And it's kind of cool. It's sort of like an Arduino-looking kind of thing or a Raspberry Pi-looking kind of thing. And the idea is we could build some stacking boards that will go on top of this that you could swap out various things. So I have an idea that we'll have one board that has the mouse and keyboard interface and things like Sega Genesis joystick interfaces on it. That could be the I/O board. Ideally, I would like to add MIDI to it, inspired by the Atari 1040 ST. That might be a little bit tricky with this crystal because the clock rate that MIDI uses isn't a nice divide down of this 3.68 megahertz clock. This chip itself can actually be clocked up to 8 megahertz, so that's maybe something that would want to look into. It has a USB connector that you can hook up to a regular PC. It has a FTDI kind of chip on it to convert USB to serial to program the chip without having something separate, so that's convenient. And let's see what else it has here. Oh, of course, it has a bunch of connectors. It has 32K of static RAM built in. You could plug a flash ROM chip in here. It has a couple of sine wave generators built into the chip, which is kind of interesting. And these aren't toggle on and off typical square waves that you would get from a primitive computer sound interface. It's actually, I think, a 32-bit DAC. I can't remember exactly, but it actually would generate some sine waves. Let's see what else. Oh, and there's various connectors for various bits of I/O. So the idea is we could make some stacking boards, and one of the boards would be a video board. So I'm thinking of one based on the TMS 9918 that was used in the ColecoVision and, of course, the TI 994A. And I think a variation of it is in the Sega Master System or one of those Sega kind of consoles, maybe the earlier one, Sega S1000. I can't remember exactly. Anyway, and then you would have a soundboard you could add on for higher quality sound than you could get from the sine waves. And for that, I've looking at the chip that was used in the Neo Geo. I have some of those. That's a pretty complicated chip. So I also ordered some of the YM2149. That's similar to a General Instruments, I think, AY something something chip that's used in a whole bunch of old video games and consoles and computers and things. So that's the general idea. So what I would like to do is take a look at the various bits of I/O that we have here and start plotting out the sort of things we can do. So as usual, you have a bunch of data pins and address pins for a microprocessor. You also have a bunch of pins labeled like P71 and P25 and P27, et cetera, et cetera, et cetera. And these are basically input-output ports. Now, you actually have a bunch of potential I/O that's not shown here. So all of the data lines and address lines, these are also ports 0 through 3, just like we have port 7 here and we have port 4 up here. Each of the ports on the 65265 has 8 bits labeled 0 to 7, as you might expect. And the problem is that the ports 0 through 3 are multiplexed with the address and data pins, and there's no way to split those out. There's one bit you set that says, are these address and data pins, or are they I/O ports 0 through 3? You have to do all or none. So there is a little bit of built-in RAM on the chip. And if you could do a microcontroller task of some sort with that tiny, tiny bit of RAM, I think it's less than a kilobyte, that's available on the chip, well, you could set that bit to have all of these pins that are labeled data and address here. You could have all of those be sort of microcontroller style GPIO. But if you want to have any external memory, you have to get the whole shebang. You have to use everything. So we're wanting to build something that's more like a regular computer or game console than some sort of microcontroller application. And more to the point, the dev board that we're using uses external RAM. Well, all of these pins that have address and data, all of these pins that have external address and data information on them, those aren't going to be GPIO. Also, P25 through P27, these are also going to be address pins, so we don't have access to those. Now, the rest of the available peripherals, those are available over here on this P4, 5, and 6 connector. So let's take a look and see what we can get out of that. So I have done a bit of research on this, trying to figure out what we can do here. And let's see if I can figure out how to make annotations using, what is this? Preview. That's what I'm thinking of. Okay, so NMIB is a negative edge-triggered interrupt. And it turns out that the PS2 standard for mice and keyboards uses a negative going clock. And it turns out that the PS2 standard for mice and keyboards uses a negative going clock. If you'd like to know more about how the PS2 interface works, I would recommend this amazing video by the quite amazing Ben Eater. PS2 is a little weird. Whether you're going from the device to the host or host to the device, the clock is actually handled by the device. So that's kind of interesting. Anyway, as a result, why don't we let the keyboard clock signal be on pin 3 on this J3 connector? So that's pin 40. So there's a register somewhere that we can set to indicate if we're using this pin 3 as a regular GPIO kind of thing, like P40, or if it's specifically being used as sort of the main non-maskable interrupt. So let's do that. Let's see. We're also going to need some sort of GPIO input for the keyboard data. Let's use the pin next to it, this P42. It's not used for anything else, so this will be keyboard data. Okay. I would also like to be able to handle mice. So one of these GPIO pins down here can also be used as a receive or, let's see, let me look. I have a paper version of the datasheet I took some notes on earlier. Here we go. So it can be used as a receive pin for a UART type of serial connection. Well, this is a pin that we could also use as a negative going interrupt. So P64 can be set as a negative edge triggered interrupt. Let's see if I can spell interrupt. Interrupt. Okay, there we go. So if we do that, let's then use that for our mouse clock. All right, so that's P64. Now, once I've done that, this particular serial port that we have, serial port number 2, here's the receive and the transmit, and there's other pins associated with that serial port up here. Those aren't available to us anymore. I mean, this pin is available for general purpose input output, say P65, but we're not going to be able to use that UART anymore. So I want to keep some of these open to be able to handle MIDI, potentially. Or maybe, if we really want to get wild with it, drive an old school printer, serial printer, or something like that. So why don't we, let's see, the clock is here. Since we're already using up what's for UART number 2, let's let P65 over here, let's let that be our mouse data. How about that? And just for reference, there's a positive edge triggered interrupt. Let me write that as PEI, or positive edge interrupt that's available on pin 66. There's another negative edge triggered interrupt that's available on pin P60. Let me clarify. So this is pin 9 and pin 3 on this connector, but it's P66 and P60 in terms of the way the I/O ports are listed in the documentation. Let's see. No, I meant to move that one. There you go. Oh, and whoops, sorry, I got this backwards. I just checked against the paper data sheet I have over here. The positive edge interrupt is available on port 60, and the negative edge interrupt is available on pin 9. So just to emphasize that that's what this mouse click is. And just for reference, there's another negative edge interrupt available on port 57. And if you want, you could also have a positive edge interrupt available on pin 56. In theory, there's a problem, though, in our specific case for the SXB. So you remember that USB port that has a connection to this serial to USB converter over here? Well, the serial to USB that it uses to talk to the microcontroller, that's what you can use to upload code and also talk to the monitor. There's actually a built-in ROM in here with a primitive monitor program you can use to type in code by hand and run code and check out registers and whatnot. That actually uses serial port 3 on this. So as a result, pin 9 and pin 10 on both J4 and J5 are unavailable to us. So let me actually cross these out to remind us that we can't really use them. And let's see. I'll make a note here that the USB interface uses serial port number 3. And look, I have this nicely color-coded to indicate that's why we can't use those pins. Okay, let's see what else is unavailable. The ROM, if you do insert one, can be up to 128 kilobytes, but I don't think all of that is available at once. Yeah, this adds up to 32K, so it looks like that's only available in 4 32K chunks. So how do we pick those chunks? Ah, here we go. So we have 120 KB of flash ROM that's mapped as the upper 32K of memory with overlays off of 2 I/O pins. So that's P43 and P44. And if you look at the schematic for the SXB board and you find the flash ROM, you'll see that the 2 highest address pins are hooked to that P43 and P44. Let's see, so this is ROM select. Oh, I need to select it over here. Okay, so this is one of the ROM select lines, and this is another ROM select line. So let's talk about the remaining interrupt pins. The sound chip I'm looking at is the YM2610 that was used in the Neo Geo. It's one of the more advanced chips of its kind that Yamaha made, and I was probably overly ambitious by picking such a chip. It's apparently very similar to the YM2608. Part of the reason I'm saying I'm overly ambitious is it does not have a very thorough data sheet. This was translated from the Japanese. But just looking down here a little bit, I see that it does have an IRQ line, so it looks like it will want to request an interrupt from the microprocessor. Let's scroll down here a bit. The interrupt signal's output is an open drain output. That means that if it doesn't want to interrupt, it lets go of this line entirely. So you'd usually have a pull-up resistor to plus 5 volts. If it does want to interrupt, it will pull the line low to ground. Now, this open drain, that is the term for CMOS circuitry. For TTL circuitry using BJT transistors, you'll typically hear this called open collector. Even when people are using CMOS chips, they'll often say open collector instead of open drain, just out of habit. Now, what do these interrupts do? I bet there's some timers on the chip. So let's search for timer. Timer. Timer A, timer B, timer. I bet you that's what does the interrupting. Maybe there's some other stuff that does the interrupting. Who knows? I'll have to look at that later. These Yamaha sound chips all have a lot of things in common, so let's look at some other ones to get some insight. So here's the YM2203. 2 programmable timers. Is there an interrupt request? Yep, there's an interrupt request pin. Timer. Oh, notice that the IRQ line here is driven by the timers. Here's another Yamaha chip, the YM2612. There's an interrupt request line. Interrupt signal issued from 2 timers. So I bet you that's fairly standard. So I found this nice web page on the TMS9918, which is the main graphics chip that I'm looking at. I'm also looking at some variations like the more advanced 9958, V9958 by Yamaha. The original 9918 is by Texas Instruments. Let's look up interrupt and see if it wants to interrupt things too. So in star, that indicates active low, CPU interrupt output. If enabled interrupts are sent each time a frame is completed. Okay, so that lets us do some tricks. We might want to be able to know about that. And this technical data book for the 9958, which came out later and is a more advanced version of the 9938, basically just gives the differences between the 2 chips. And if I search for interrupt, all I see is a mention of it in the pinout, so I suspect the behavior there is the same. Okay, so first glance, I have this level sensitive interrupt request that's active low. I have another interrupt here, a positive edge going, so I could use one of them for the video and another for sound or vice versa, but one of them is going to have an inverter on the input. But pausing the recording for a bit, I realized I made a mistake here. So this is not actually edge triggered. It is active low, but it's active low level sensitive. So it's more along the lines of what IRQ is. So let me actually write here that NMIB and IRQB are active low level sensitive. So kind of like negative going edge, but without the edge part. Now, what I'm thinking is let me actually take the keyboard clock and move it down here. So let's see. Something like this. And then let me take the keyboard data and move it down here just to kind of line up and be consistent with the mouse data, because that's kind of fun. Actually, let me move that over like this. Something like that. Now it looks slightly less disgusting. How about that? Maybe I'll move this here. All right. Hopefully that indicates what's going on. And let me make a note here that keyboard is connected through an inverter. And actually, just for the purposes of testing, I think it'll be natural to put the keyboard where we don't need the inverter because we'll start testing with the keyboard and then eventually go to using the mouse. So let's do something like this for now. Now, eventually, once everything's working, it doesn't really matter much which one we use for which, but I just think for testing, it'll be most natural not to go through an inverter, just to make it easy to breadboard or whatever. All right, let me clarify. Mouse clock is connected through an inverter. And now these lines up here are available for the video and the sound interrupts. Notice this is a NMI non-maskable interrupt, but because it's multiplexed with this P40 pin, I could hit the register and just make it a standard GPIO and effectively mask the interrupt. There may be some advantages to having the masking done in the actual IRQ mask register that's sort of built into the 65816 architecture itself versus the 265 architecture that's added around it. I don't know. Haven't really looked into that. All right, so one of these can be sound and one of them can be video. It's kind of arbitrary. So let's make this sound interrupt request. Maybe put that here. And the other one will have BR video interrupt request. And these are both open collector style outputs and they're active low. So that works out. Now I would like to have a serial port available. So let's just call this serial 1. And there's only one serial port left. That's serial 1, which is why I'm calling it serial port 1. So here's the data receive, data transmit of serial 1. And let's see, what are these things? The DTRB and DSRB. So if we look at the chip that does the conversion between USB and serial, here we see the transmit and receive for serial port 3 for the monitor console. And it looks like this. Oh, wait, sorry. Here's receive, here's transmit. Here's that DSRB, and here's that DTRB. So it looks like that's additional hardware handshaking information. Now, this DSR and DTR, as far as I can tell, that doesn't appear anywhere on the actual data sheet for the processor itself. So this looks like something that is user-defined for this particular board and configuration. Yeah, so it looks like these are just GPIO pins that they're using for a particular purpose here. And I suppose the monitor probably has some built-in routines to use these sort of things. In any case, if you're using something like MIDI, if you're using the serial for something like MIDI, I think you could just transmit and receive. I don't think you need any other handshaking signals. But let's go ahead and stay away from pins 5 and 6 on J4 for now. So this person, Adam, put together a really nice page about the PS2 protocol. And if you want to transmit from the device to the host, which is most of what you typically do in PS2, that's pretty straightforward. It is all the stuff that we've talked about so far. Both the clock and the data lines are open collector buses, so you use a pull-up resistor to tie them high, and either the device or the host can pull either line low. Interestingly, regardless of which direction the data is going, the device always does the clocking. Now, what happens if the host wants to send information back to the device? That's a little bit more complicated. Essentially, what the host will do is the host will pull the clock line low, and that tells the device that the host wants to send data. The device then triggers the clock line, but instead of the device putting data on the data line the way it usually does, the device will then clock in data that is sent by the host. Yeah, it's confusing, but it's actually pretty clever. And you can see there is an inherent asymmetry into how easy it is to transmit one way versus the other way. Before the device sends information to the host, it always checks the clock line first to make sure that it's high, to make sure that the host isn't wanting to transmit. So if we do want to be able to send data from the host to the device, from our computer to the mouse or the keyboard, to do things like turn the caps lock or the num lock light on or off or something like that, then we need a couple of more pins. We need one for the mouse and one for the keyboard. To parallel with the mouse clock and also go with the theme that this is something that is hitting the clock line, let's make pin 3 on J4. Let's make this the mouse assert. So this is when the host, the computer, wants to send data back. All right, so then we'll, no, that should stay there. Let's see. This is the one that should move. All right, so pin 7 here, this is going to be the keyboard assert. Let me shorten that just so it doesn't get confused with whatever we're going to do with P71 over there. All right, let's see. Oh, let's clean that up a little bit. Now, there is a problem here in that the microcontroller, as far as I know, doesn't have a facility for tri-state outputs. So ideally what we would have is a register that we could flip that would say, okay, if we want to assert this, pull the line low, but if we don't want to assert it, just leave it disconnected entirely. I don't think we can do that. I think it will output a 5 volts if we're in the other logic state from the 0 volts, and that will cause all sorts of problems because we'll have the device and the host possibly trying to force different logic values on the same line. So going to the 74 series logic entry on Wikipedia, we need some sort of logic gates with an open collector output. Let's see, a 7405 hex inverter gate that will do. Or for that matter, we could use a 7401 or 7403 NAND gate. Wait, there's 2 of these? Quad 2 input NAND gate. Quad 2 input NAND gate. Maybe this is supposed to be a NOR gate? Ah, yes. Quad 2 input NAND gate. So, quad input 2 input NAND gate. Why would you have that and the 7401? Are these the same thing? Quad 2 input NAND gate with open collector output. Let's look up 7401. Quad 2 input NAND gate. Huh. How are these chips different? Oh well, I'm not going to worry about it now. Anyway, you could take one of these NAND or whatever gates and you could tie the inputs together. Which gate you pick may largely depend on what you happen to have in your parts drawer, or it may depend on what other kinds of logic you might need elsewhere in the circuit. Basically, we'll be looking for things that have this open collector column marked. So let me make a note of that. We'll say that the assert lines, we'll say that the PS2 assert lines must go through a gate with an open collector output. All right. Let's see. So we do have some I/O left. We have 1, 2, 3, 4, 5, 6 GPIO pins left. What should we do with those? I would like to be able to include a couple of Sega Genesis joystick connections, and these are fairly simple. Mostly the main thing that gives it a little bit more complexity is that there's an actual output line to the controller that is a select signal that, depending on whether it's false or true, logically speaking, ground or plus 5 volts, gives you a distinction between the A button and the B button, or the start button and the C button. The up and down and select buttons. Oh, this is weird. Notice I have ground left, ground right. Why isn't this just left right? Oh, you know what? You can't hold down left and right at the same time. So if you put the select pin at ground, you wouldn't be able to read ground on both of these at the same time, because you can't press left and right at the same time, remember that, like most controllers like this, all of the various buttons are connected through a pull-up resistor to plus 5 volts. So when you press a button, it's pulled down to ground. There's no way to pull both of these ground at the same time. So if you put your select at ground and you read ground at both of these, it tells you you have one of these 3-button controllers and not an older 2-button controller like with the Sega Master System. And speaking of which, if we look at the pinout of the old Sega Master System controller, oh, look, advertisement. Is there a way to make this not be difficult? Okay, so we have up, down, left, right, and then button B and button C would correspond to, I guess, button 1 and button 2 on the original Sega Master System controller. And the select button, I guess, would correspond to this light sensor. I suppose that's probably some sort of light gun for shooting games of some sort, like Duck Hunt on the Nintendo, whatever the Sega equivalent of that was. And a game that really only needs 2 buttons could be programmed to handle both kind of controllers, because you can use this little trick to figure out which kind of controller is plugged in. Oh, something we should find out is if the Genesis has built-in pull-ups for these inputs or not. Oh, actually, I guess it doesn't really matter. So the 74HC157, that is going to provide solid true or solid false outputs. And it's being driven by this 5-volt power supply here. Now, the Sega Master System controller, if you plug that in, there's no voltage being applied to it, so it probably is relying on pull-up resistors on the console itself. So, to handle both controllers, we should include some pull-up resistors, and then the controller here can pull those lines down if it needs to. So let's do that. Now, Genesis has a 6-button controller option for more complicated games like fighting games, and as this developer found out, that 6-button controller is immensely complicated in a way that doesn't really make sense until you realize that they needed to make it compatible with the 3-button controller. And basically that select pin, instead of just being low or high and hitting a multiplexer, you actually have to toggle that pin. And depending on how you toggle the pin, you will put the controller in different states, and then you can read different kinds of information from it. And it's immensely complicated. The main important thing we need to know here is that our existing setup of being able to drive that pin 7 select, that will work for the 6-button controller. Dealing with it is just a matter of some more complicated software. Okay, so we have some GPIO pins to choose from. Let's see, we have sound and video up here. Just to go along with the theme, we have user interface stuff on connectors 4 and 5. So how about, let's make P51, let's make P51 our controller. Should we call them controller 1 and 2? Sure, why not? We'll make that the controller 1 select for the, let's call it control. How about that? All right, and we'll call this controller 2 select. So that selects which particular buttons we're reading. The input will still do on the data pin side. So we'll actually read the buttons using D0, blah, 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 blah. Now, we need some sort of chip select for everything. So we need a chip select for the sound chip, a chip select for the video chip, and we need a chip select for each of the controllers, because each of those is going to have some sort of 573 style latch. Now, I do have 4 GPIO pins left, but it feels kind of cheesy to use those as chip selects when we have some chip select address decoding functionality built into the 265 microcontroller. Now, I used some GPIO to toggle the select pins, instead of using the data pins here, because for reading from the joysticks, we have to read a bunch of data at once, but really this is 2 bits. So it seems overkill to deal with a bunch of logic that might be sitting on our board that would have to put there to handle data going the other way. Okay, so let's take a look at these chip selects. Okay, so it looks like chip select 7, 6, 5, 4, and 3 all have to do with memory. So yeah, later we'll want to add more memory to our system, sure, but we won't worry about that right now. All right, so chip select 2, this looks like it has to do with a bunch of internal register stuff. I can't imagine that that's actually terribly useful. All right, so that leaves us with chip select 1 and chip select 2. So it looks like if we write to this DFCO to DFFF address space, that's 64 possible locations, that will activate chip select 1. And I should mention that you need to select an appropriate register and set it appropriately in order to have this chip select action be working. Otherwise, you could use it as just a standard GPIO pin. Same thing for chip select 0. You have the option of whether using it or not. We're probably going to use both. All right, and then external chip select 0, this looks like it's toggled when you write to DF00 and DF1F with some caveats. So the caveat is that, there's some control register where the first 8 bytes of this are used for internal I/O registers. And if you're using them for internal I/O registers, then it doesn't hit the chip select line. All right. But it looks like you can not use those internal I/O registers and hit the external memory bus. You know what? We should really dig into this BCR0 register and figure out what it's doing. Okay, so BCR is an 8-bit register, and it decides, are port 0, 1, 2, 3, 4 I/O pins, GPIO, or are they address and data bus pins? They are address and data bus pins. We have external memory. So BCR0 is going to be equal to 1. And then if we look over here, if BCR0 is equal 1, external memory bus is enabled. So it's active for everything. So we have this full range available, this DF00 to DF1F. If we access that, that will trigger chip select 0. Okay, so we could use one of these maybe for the video and sound chip and use another one for a couple of joysticks. And then within there, maybe use one address line to pick either the video or the sound chip or which joystick. And then for the video chip and the sound chip, we need at most 2 address lines based on the data sheets that I've looked at to select registers in those chips. Actually, the TMS9918, we actually only need 1 address line, but the later Yamaha chips, the V9938 and 9958, those actually require 2 lines, and all of the sound chips just require 2 lines. As an example, here's the 2160 datasheet. We see 2 address lines used to select various registers that you can either read or write from when the chip select line is asserted low. Let's look here. See A0, A1. And here is the 9958 datasheet. We have mode 0, mode 1. Anyway, we need 2 lines that are hooked to our address bus on our CPU side. So I have 5 lines available here, and I have 6 address lines available here. And so it looks like that's plenty. And it looks like the remaining address decoding is going to be very simple because it just involves picking one device or another. So we've avoided having to use a ton of logic chips or use some sort of GAL-type programmable device. Of course, we might want to change that later if we need to add other sorts of peripherals, but in any case, I still have 4 GPIO pins left free, so I think that's kind of nice. Okay, just to have something, let's say that chip select 0 is for the controllers. Yeah. And chip select 1 is for audio video. So that's for the sound chip or the video chip. And within that, let's see, for future expansion, if we eventually want to add something like a 6522 versatile interface adapter, a VIA, or something like that, that can need up to 4 address lines to select register. So how about, let's take a look and see how much address space we have. Okay, so we have 6 lines here, 5 lines here. Just to be consistent, let's let A5 be a select line. And so we'll say something like, for A5, because we're running out of space here, maybe A5 equals 0 indicates video, A5 equals 1 indicates the sound chip. Of course, this is for CS1 asserted, i.e. it's low. Oh, not A5. Let me make this A4. I want 4 address lines just open as a general philosophy. So that's A0 through A3. And then what about for CS0 asserted? That's for the joystick. A4 selects the controller. And then I can leave it as an exercise for the viewer, i.e. my students, to figure out what addresses here for the 2 chip selects map to these various selections. Notice that there's some bits that are kind of unused. So multiple addresses you could write to or read from would. Of course, those memory mapped I/O locations would start to have less redundancy as we add more peripherals. And the remaining address decoding would get more complicated. But I think we could do a lot of interesting things with just the various devices we've included here.